So let's take a look at some specific examples of force applications and how to actually apply some strategies to solving problems. So the first thing you want to do in every single problem is list everything that you're given. And that includes listing any relevant equations that might help you to get to your answer. Next, you want to kind of draw a picture because physics is all about motion. We should be able to picture a lot of the things that are happening, at least in this first semester of physics. So with forces, we want to do this with the so-called free body diagram, but we can kind of use this strategy in any kind of physics problem. Third, we want to apply Newton's second law. So we want to apply that the sum of forces is equal to the mass times the acceleration, and or any kind of kinematic equations. So those kinematics that we learned earlier in the semester, those are back. They are not going anywhere, and they will be with us for a long, long time. And then 4, occasionally, sometimes you can check your solution and check your answer and see if you got the right thing. So let's take a look at a general example of how we would do a tension problem. So what we have here is 2 attached blocks. Block number 1 is attached to block number 2 through this rope that goes over a pulley. They're both accelerating at these accelerations, and we are asked to find what is the acceleration of each of the blocks and what's the tension in the string in terms of M1, M2, and G. So what that means in physics is M1 is now something we can treat as being a known value. M2 is a known, and G, well, we know what G is. G is 9.8 meters per second squared. Okay, so we can think of all these things as just being some number. It can be any number. It's a constant number, and it's a given. So these are all the givens that we have. So how do we start solving this problem? So what we've done here is we've made a list of everything that we know. Now we need to make equations, but to really understand equations, oftentimes we kind of need to intermingle step 1 and step 2. So we need to draw a picture of what all of this looks like. And I can do that by drawing a free body diagram. So we have mass 1, and mass 1 is going to experience some forces acting on it. Mass 1 is going to have the force of gravity pulling it down. So that's going to be the force of gravity, also equal to the weight of block 1. And then we also have a couple other forces acting. We have the normal force. The normal force is going to act exactly perpendicular to the surface that we're sitting on. So that acts straight up, completely counteracts gravity. And then we have the force due to this rope. And the force due to this rope that's attaching the blocks is going to be tension. That's kind of acting off to the side. And then we have some motion going on here. We have this motion, some acceleration 1 that's going in that x direction. Then what else do we have? What other kinds of forces do we have? What else goes into our free body diagram? We need to do all of this again for block number 2. So here we have block number 2. It has a mass. We'll call that mass M2. It's got the force of gravity pulling it down. Right, so we've got that arrow yanking it down. W2, the weight of the second block, also equal to the force of gravity of block 2. Then we also have this rope that's pulling it up. That rope is going to be tension. It's the same exact rope as the one that's on block number 1. So that tension on block number 1 is going to be the same as the tension on block number 2. And that's going to be a key point. And we know this block is moving, it's accelerating downwards. And then the other forces, well, block number 1, it had this normal force acting on it. But the normal force is all dependent on sitting on top of a surface. And block number 1 is sitting on this table. Block number 2 is sitting out in air. So since it's sitting in air, there is no normal force. So we don't have a normal force on block number 2. And these are all the forces that I have. So now what do? Now is where I can start drawing some equations. I can start writing some equations down. And we can do this treating each block a little bit separately. So block number 1 has some forces going on with it, and block number 2 has some forces going on with it. So we can write the sum of forces acting on this block is going to be equal to the mass of the block, mass 1, times the acceleration of the block, acceleration 1. So what I need to do now is really write down what are these sum of forces that are acting on this block. If I look at my picture, I can see that in the x direction, so moving left and right, the only force I have here on block 1 is tension. So that's what tension is going to go. Tension is equal to the sum of forces, and that's equal to the mass of block 1 times the acceleration of block 1. Now we could do the same kind of steps. Make a little bit of space here, and we do the y direction. So what's happening in the y direction for block number 1? I do the sum of forces again. That's going to be equal to the mass times the acceleration of 1, this time in the y direction. Now if I look at this, going up and down, this block isn't bouncing up and down on this table. It's not bouncing as it's going. It's not a wobbly path. It's just going straight entirely in the x direction. So that means that the sum of forces on this has to be equal to 0 because there's no acceleration. So my sum of forces, because I'm not moving in the y direction, has to be equal to 0. But I do have forces, right? I've got the normal force that's going up. So I have the normal force pulling me up, and I have gravity, the force of gravity, that weight, pulling me down. So I have the normal minus the weight of block 1 has got to be equal to 0. So I now know that the normal is equal to weight 1, or the normal is equal to mass 1 times gravity. And now I'm starting to see that I'm starting to get variables that are in terms of constants. So the normal force is in terms of mass 1 and g. So if I was asked to find the normal, those are givens, mass 1 and g. I would be done with the problem. So let's do the same process, same exact procedure for block number 2. For block number 2, we look at the x direction, and we see sum of forces in the x direction for this is mass 2 times the acceleration of block 2 in the x direction. There's nothing moving in the x direction. So sum of forces in the x direction for block 2 has to be 0. And if I look at this, look over at this block 2 going side to side, there's nothing going on. So there's 0 forces, and I just proved 0 is equal to 0. Good for me. Now I move on to the y direction. In the y direction, again, Newton's second law, sum of forces, is equal to the mass of block 2 now times the acceleration of block 2 entirely in the y direction. Now I have to be a little bit careful here. And I have to pick some directions. Okay, I have to pick what directions I want to be positive and what directions I want to be negative. Thus far, in all the physics that we've been solving, we've been tending to say anything that's going down is going to be negative. This acceleration is going to be negative because it's going down. So let's write my sum of forces now. Sum of forces has to be equal to mass 2 times acceleration 2 with a negative. Again, because this is going down, and I'm choosing down as being the negative direction. So let's write out the sum of forces we have. Any forces that are going up are going to be positive, so that's tension. Any forces going down are going to be negative, which is weight 2. And that's going to be equal to negative mass 2 times A2. Okay, so I can write this out a little bit more. I have tension minus mass 2 times gravity, that's what the weight is equal to, equals negative m2 times a2. And now I can come up here for block 1 and I recognize tension is mass 1 times a1. So I can take that and I can plug it in to see that mass 1 times acceleration 1, again plugged in for t, minus mass 2 times g is equal to negative mass 2 times a2. And I'm starting to get closer. I'm looking for acceleration. What is the acceleration of this? And I want it in terms of the variables m1, m2, and g. This is my goal. I have m1, I have m2, I have g, and I have 2 accelerations. So what do I do with this? And this is the key behind these kinds of tension problems. So because this string that is connecting these two things, this string is taut. It's tight. It's not flexing and it's not stretching. So that means that every single part of this string has the same acceleration. So the acceleration of the string over here by block number 1 has to be the same as the acceleration by block number 2. That's because this string is not stretching. So because of this fact, because they don't tell us the string is stretching, we can assume that the tension everywhere is the same and A1 is equal to A2. So I'm going to say that those are both just equal to each other. So now I can take this and I can plug in A everywhere I see A1 and everywhere I see A2. The accelerations of both blocks have to be the same. So I have mass 1 times acceleration minus mass 2 times g has to be equal to negative mass 2 times a. Now this is just algebra. I need to get everything all on the same side. So I move my mass 2 over to the left-hand side. Mass 1 times a minus mass 2 times g plus m2 times a is equal to 0. I want to isolate my a's, so I move my mass 2 times g to the other side. Mass 1 times a plus mass 2 times a equals mass 2 times g. Again, that was by adding mass 2 times g to both sides. So this is basic algebra, and we should be hopefully getting pretty good at this by now. I have an a in common between these two terms, so I need to factor that a out. So I have a times mass 1 plus mass 2 is equal to mass 2 times g. Now I can divide both sides by mass 1 plus mass 2. And this is the hard part of physics. It's the algebra. Never the calculus, never the equations, always the algebra. These two mass 1 plus mass 2 cancel out. And the acceleration is mass 2 times g divided by mass 1 plus mass 2. And there we get our final answer for the acceleration in the event of a tension problem. So important things to note were that tension was the same at all points along the rope, and because that tension was the same, acceleration was the same at all points in the rope. And that's kind of a sample of how to use tension in physics.